Hello everyone and welcome back to Educator.com. I'm Dan Fullerton, and in this lesson we're going to talk about retarding and drag forces. Yep, you've got it. We're actually going to get to air resistance. So our objectives are going to be to find the terminal velocity of an object, to describe the motion of a particle under the effect of a retarding or drag force in terms of its displacement, velocity, and acceleration, use Newton's second law to write a differential equation for the velocity of the object, derive the equation for velocity from Newton's second law using separation of variables, and determine the acceleration for an object falling under the influence of drag forces. So let's start off by talking about these retarding or drag forces. Sometimes the frictional force is a function of how fast an object is going, its velocity, and air resistance is a great example of this. These forces are called drag or retarding forces. Now, as we go through our analysis of drag, this is going to be our first lesson in a while that's going to get pretty heavy into the math and calculus. Probably seeing some things, if you're taking calculus concurrently, where you're seeing it in physics before you might in calculus. That's okay, it's not uncommon. Do your best to stick with it, and then come back to this lesson later on once you're a little bit more solid on the calculus and some of the integration we're going to be doing. So that's not uncommon at all. If you leave this lesson a little fuzzy, that's okay. All right, so let's start by talking about a skydiver. Assume we drop our dear friend Alex from an airplane. Typically, the drag forces on a free-falling object take the form where the force of drag is some constant times the velocity, or a constant times the square of velocity, or sometimes even something in between that, but where B and C are constants. For the purposes of this problem, let's assume that the drag force is equal to a constant times the velocity. So let's draw a free body diagram for our dear friend Alex, who we're about to push from an airplane. We have the weight of Alex pulling him down, and the drag force back up. And we'll call down the positive y direction, since that's the way Alex is going to start his motion and finish his motion. So as I analyze this, the net force in the y direction, using Newton's second law, is going to be mg minus the drag force. And that's all equal to mass times the acceleration in the y direction. But we just said that our drag force is equal to bv. So then we could write that mg minus bv equals ma. Now let's take a look at what happens when we first push Alex from the plane. Initially, at time t equals 0, Alex's velocity is 0. Therefore, the drag force is 0, mg equals ma, and a is just equal to g. The acceleration is equal to the acceleration due to gravity. So therefore, we can write at that point, acceleration is equal to g. Now, as t increases, as we head toward infinity, eventually, Alex reaches a maximum or terminal velocity. Terminal velocity. We'll abbreviate that Vt, and at that point, acceleration is equal to 0. So at that point, all the forces must be balanced if there's no acceleration, so the drag force must equal mg at that point. So when we go to our Newton's second law equation, we have mg minus bv equals ma, but when we're at the condition of terminal velocity, acceleration is 0 and v equals vt, so our equation becomes mg minus bvt equals 0. Therefore, we can solve for terminal velocity and say terminal velocity is just going to be mg divided by that constant b. So a formula for terminal velocity based on that constant in our f drag equals bv equation. And we also know initially at t equals 0, velocity is 0 and acceleration is equal to the acceleration due to gravity, g. And I think that'll set us up to get into our math using our Newton's second law equation. So if we go back to our Newton's second law equation, which has velocity and velocity's derivative, acceleration, in it, we really have two different forms of the same variable in the equation. The variable itself and its derivative, and that's called a differential equation. And we're going to solve that using a strategy known as separation of variables. So let's start on the next page to give ourselves all kind of room here.